Okay, so in this video we're going to solve a slightly different kind of weak acid problem, and that is for a diprotic acid. Diprotic acid means it has two protons that we can lose, so if we take a look at this, we can write out the dissociation equations, and it's actually a stepwise dissociation of two. So the first one is going to be the aqueous carbonic acid here, H2CO3, and that is going to dissociate at equilibrium into H plus and bicarbonate HCO3 minus. Okay, and then furthermore, the second dissociation is going to be that bicarbonate HCO3 minus. It can dissociate into H plus and CO3 2 minus. So the way you deal with this is we first solve the top reaction and find out what's happening as we break the carbonic acid into bicarbonate, and then we're going to deal with however much bicarbonate we make, what part of that is going to go and dissociate further. So in order to do this, we need two Ka's. We need the Ka for H2CO3. Okay, so if you look up for a chart, that's what you're looking at. Sometimes it's called the Ka1 and the Ka2. The Ka2 in this case would be the Ka of HCO3 minus. Alright, so we're going to set up a Rice chart. We're going to do this top one first, the carbonic acid. And our initial concentration, 0.10 molar, 0, 0. And for the change, right, minus x, plus x, plus x. So sort of typical here, just like a regular weak acid, 0.10 minus x, x, and x. So what we're going to end up with then is that we're going to just set up the equilibrium constant x squared over 0.1 minus x equals, and the Ka for H2CO3 is 4.3 times 10 to the negative 7th. Now with that Ka being so small, 10 to the negative 7th, we could just do the approximation and not worry about the minus x right here. 0.1 times 4.3 times 10 to the negative 7th, take the square root. You can also feel free to plug that in and do a graphical method. If you do this out, the number comes out so small that percentage-wise we're fine doing the approximation here. And therefore we're going to solve that, and it comes out that x equals 2.07 times 10 to the negative 4th, so going to 2 sig figs, we'll call it 2.1 times 10 to the negative 4th. Oops. Bad 4 there. Okay, so now this is the concentration of the H plus, concentration of the HCO3 minus moving forward. And that means that when I set up the second Rice chart down here for the HCO3 minus, my initial concentration of that is now 2.1 times 10 to the negative 4th. That's how much I just made. And likewise, when I get to the initial concentration of H plus, I can't really assume it to be 0. It's 2.1 times 10 to the negative 4th. It's never really 0 either. You need to keep in mind that this whole time that we've been doing this, the initial concentration of H plus, there's always that 1 times 10 to the negative 7th if you're adding something to water. It's just that usually that amount is so small in comparison to everything else that you don't really need to worry about it. It'll just wash right out in the sig figs, and it's not going to play a major role. You can see right here, it's 3 orders of magnitude below 10 to the negative 4th, so that's a pretty small amount. So now we're going to set up the change. In this case, I'm going to use y instead of x. Call it minus y plus y plus y, just to be able to differentiate between the two. 2.1 times 10 to the negative 4th minus y, 2.1 times 10 to the negative 4th plus y, and therefore when we go to solve for it, we have y times 2.1 times 10 to the negative 4th plus y divided by 2.1 times 10 to the negative 4th minus y. Now again, you can go ahead, plug this in, set that equal to Ka for HCO3 minus, which happens to be 5.6 times 10 to the negative 11th. Okay, and if you plug that in, you're going to solve for y, do it graphically. You actually get y equals, oops, change color here to make it easier to see. Okay, y is equal to 5.6 times 10 to the negative 11th. Now note, this is the same as the Ka. Right, the Ka, make that more readable. Tough time, new stylus today. So 5.6 times 10 to the negative 11th, you can see that's equal to the Ka of HCO3 minus, the one we just said equal to. And the reason for that is that if you take a look right here, 2.1 times 10 to the negative 4th plus y is so small, and minus y, that those are both 2.1 times 10 to the negative 4th. So realistically, 2.1 times 10 to the negative 4th plus a very, very small number over 2.1 times 10 to the negative 4th minus a very, very small number is 1. And therefore y is equal to the Ka. So that's what we get here. All right, so now we are in the right place to be able to answer the questions that we're given. The first thing we're going to do is go ahead and do the pH. So the pH equals the negative log of concentration of H+, right? Well, concentration of H+ is technically two things here. It is the X plus Y. So realistically, the concentration of H+ is this, 2.1 times 10 to the negative 4th plus 5.6 times 10 to the negative 11th. If you do that out, it's just going to be 2.1 times 10 to the negative 4th. 10 to the negative 11th is so small, it's not going to factor into this calculation at all. So therefore, the pH, plug that in, pH equals negative log of 2.1 times 10 to the negative 4th, or 3.68. Okay, so that's the first part. And that tells you that for most diprotic acids, as long as the Ka1 is so much greater than the Ka2 is a lot smaller, then really to find the pH, you're just going to have to use the first concentration of H+ that you get, that X. It's almost always going to be that. And now for the concentrations of everything else at equilibrium, we have what we need. So concentration of H2CO3, of the carbonic acid. Okay, strangely enough, it actually has not changed because we're only at a 2 sig fig, so it's changed, but at a much smaller amount. So still roughly 0.10 molar, as near as we can tell. The bicarbonate, HCO3 minus, okay, that has a concentration of 2.1 times 10 to the negative 4th, or X value. And our carbonate, CO3, 2 minus, okay, that is going to be equal to the value of Y, 5.6 times 10 to the negative 11th molar. All right, so this is how you solve a diprotic acid problem. You can do the same thing with the dibasic. It's just backwards. You're going to write two base reactions, and the first one be gaining one proton, the second one be gaining another. Likewise, if you want to do it with phosphoric acid, which is triprotic, you would just set up 3 in a chain and work your way down to find out how much PO4 3- you have.